will start Lecture 2 of the DC Circuit course on voltage, current, power, energy, and the passive sign convention. Students should be reading sections 1.4 to 1.6 of the textbook in order to stay current on this topic. The objectives are to be able to briefly and clearly explain voltage, current, power, and energy, be able to write formulas for voltage, current, and power and energy, be able to identify whether an element is delivering or absorbing power, be able to explain the difference between power and energy, be able to apply the law of conservation of energy to confirm that power balances for a network, be able to use the passive sign convention to calculate the power for an ideal basic circuit element given its voltage and current. Recall that the separation of electric charge creates an electric force or voltage. Whenever positive and negative charges are separated, energy is expended. Voltage is the energy per unit charge created by this separation. Another way of stating that is that V is equal to dW dQ, where the units are change in energy or change in joules over change in coulombs. Volts, so the units for volts are joules per coulomb. The motion of charge creates an electric fluid or current. The rate of charge flow is known as electric current. So the units for current are amperes. Amperes is equal to dq dt, or coulombs per second. So the following diagram shows current flow, I of t, versus time. The current flow into the positive terminal of an element is given by the following waveform. If the initial element is initially charged to 2 coulombs, that means Q of 0 is equal to 2 coulombs. What is the total charge transferred to the element in 5 seconds? Now we just discovered that I is equal to dq dt. However, we are given current and we want to find charge. So the way to do that is to integrate this equation. So you will have Q of t is equal to the integral from 0 to t I d lambda plus Q of 0. In this case, we want to know the charge from 0 to 5 seconds. Another way of finding the integral of a waveform is area under the curve. So in this example, we're actually not going to do the math, but we're going to find the area under the curve. So here we have a rectangle, a triangle, and another rectangle. So that area is equal to 1 times 2 plus 1/2 times 1 times 2 minus, because this one is below the time axis, minus 2 times 1. So the area is equal to 2 plus 1 minus 2, which equals 1. And that's 1 coulomb. So going back to our equation, we have that the charge transferred to the element in 5 seconds, Q of 5, is equal to 1 coulomb plus the initial charge, which was 2. So the answer is 3 coulombs. An ideal basic circuit element has 3 attributes. 1, it has only 2 terminals. 2, it is described mathematically in terms of current and voltage. And 3, it cannot be subdivided into other circuit elements. Here's the model that we will use to recognize a basic circuit element. The main thing I must emphasize here is that you always must show plus and minus when you have a voltage. Voltage is separation of charge. So to write a voltage without putting plus and minus is meaningless because I have no idea where the higher and lower potential is. Subsequently, to write a current, you always must show an arrow. To write a current and not show the arrow is meaningless because current is the flow of charge, and if I don't have the arrow, I don't know which direction the current flows. A voltage drop is when a current flows through an element from the positive to negative terminal on an element. Otherwise, it is a voltage rise. Here are some examples of voltage drops. If I have a 5-volt source and the current is 2 amps and it flows from the positive to the negative terminal, that is a voltage drop. If I have a 5-volt element and the current flows 2 amps from the negative to the positive, that is a voltage rise. There are 2 more examples. This is also considered to be a voltage drop. If I have a 5-volt element and the current arrow is drawn down here is 2 amps, that's still a voltage drop because the current came from the positive to the negative. It had to come from somewhere. Similarly, if I have a 5-volt element and I put the positive on the bottom and the negative on the top, and I draw the arrow at the top, and it's 2 amps, and it's going from the negative to the positive, that is also called a voltage rise. But it would also be a voltage rise if I have the negative on top, the positive on the bottom, 5 volts, and I show the current down here as 2 amps because the current still went from negative to positive, and that is also a voltage rise. The passive sign convention states that when the direction of current flow through an element is in the direction of the voltage drop across the element, use a positive sign that relates the voltage to the current, otherwise use a negative sign. So for the examples we have here, we would say that this element is a voltage drop, so it obeys the passive sign convention. Here we have current going from positive to negative, so we would say that this one also obeys the passive sign convention. So alternately, since these are all rises, this one does not obey the passive sign convention, this one does not obey the passive sign convention, and this one does not obey the passive sign convention. Okay, now let's look at a concept question. The charge flowing through a light bulb is shown in the figure on the right, this one here. Which of the following figures shows the current flowing through the light bulb? So this is the same equation we had before. It's a relationship between charge and current. So I is equal to dq dt. This time we are given charge and we want to find current. When you have a waveform, the relationship between the derivative and the waveform is slope of the tangent line. So when I want to find the derivative of a waveform, you find the slope of the tangent line. For the example we have here, we actually don't have any numbers, but what we do know is that here we have a positive line, here we have a negative line, and here we have a positive line. So whichever one of these figures represents the current, it must also have a positive value, then a negative value, then a positive value. So this one does not work because it's positive for all time. This one does not work because there's only one positive and one negative value. This is the only diagram that had a positive value, then a negative value, then a positive value. So that means the diagram 2 is the only one that could possibly be the current through the light bulb. The useful output of electrically based system often is non-electrical. This output is expressed in terms of power or energy. Power is the time rate of expending or absorbing energy. Power is equal to dW dt. Something I would like to emphasize here is that the units for power are watts. The units for power are watts. And the units for energy are joules. This is a common mistake that students make, is to mix up the units for power and the units for energy. So once again, the units for power are watts, the units for energy are joules, and so 1 watt is equal to 1 joule per second. The power associated with the flow or charge follows directly from definition of voltage and current, where since P is equal to dW dt, and voltage is dW dq, and current is dq dt, power is equal to V times I, and we use this equation extensively in class. P is equal to V times I, where voltage is in volts, current is in amperes, and power is in watts. If the current flowing through an element is in the direction of the voltage drop across the element, P is equal to positive V times I. Otherwise, it is P is equal to negative V times I. If the numerical value of power is positive, P is greater than 0, the element is absorbing power. Otherwise, the element is delivering power. There's something that I also want to emphasize here. You absolutely cannot tell me anything about absorbing or delivering power if you don't know the numeric value of the power. This is a common mistake students will make, is they will look at a circuit element and try to tell me whether the element is absorbing or delivering power. If you don't know the values of the voltage and current, you cannot tell me whether the element is absorbing or delivering power. The analogy I like to use for this is money. You cannot tell me that money is power and that I'm gaining power by having more money unless you know I'm getting positive money. So in other words, I have to know the numeric value. $1 is not power. $1 million may be power. So until I know the number, I cannot say that I am delivering or absorbing power. So let's look at some examples of this. So here I have that basic circuit element again. And here I have positive on top, negative on the bottom, 5 volts. And I have the current 2 amps. Since this obeys the passive sign convention, P is equal to positive V times I. So P is equal to positive 5 times 2. So P is equal to positive 10 watts. Since P is greater than 0, I would say that this element is absorbing power. Now, if I gave you another basic circuit element, and I do the current coming up and called it 2 amps, and I have negative and positive 5 volts, then here, this does not obey the passive sign convention, so P is equal to negative V times I, or negative 5 times 2, which is negative 10 watts. That means that this element is delivering power. So I have to put delivering power, but what you would say is that you have 10 watts delivered. You would never say that you have negative 10 watts delivered because that means 10 watts absorbed. So either you write the words 10 watts delivered or negative 10 watts. Negative 10 watts automatically means 10 watts delivered. Let's do one more example over here. So here I have 5 volts, positive on top, negative on the bottom, and I have a current source pointing down, but it's labeled negative 2 amps. So here, based upon the way it's drawn, I have P is equal to positive V times I. But the numeric values are positive 5 times negative 2. When I do the math, this gives me negative 10 watts. So this means I have 10 watts delivered. So the way I think about this, if money is power and I have negative 10 watts, that means I have given some of my money away. I'm delivering my power to someone else. If money is power and I have positive 10 watts, then I'm gaining more power because my bank account would be going positive, or I'm absorbing more power. Okay? Negative, delivering power. Positive, absorbing power. The law of conservation of energy states that energy can neither be created nor destroyed, only transferred. Therefore, the total power delivered to an electric circuit must be equal to the total power absorbed. Now let's look at an activity to examine this concept further. Figures 1 and 2 shows the current through the voltage and the voltage across A as basic circuit element. Sketch the power and find the total energy absorbed by the device for the period of 0 to 8 milliseconds. So remember, the equation that we have is that P is equal to V times I. So what we want to do is to multiply these two waveforms together. So first, from 0 to 2 milliseconds, the voltage goes from 0 to 40 volts, and the current is at a constant 10 milliamps. So when I take 40 times 10, that gives me 400. But since this is 400 milliwatts, I can also write that as 0.4 watts. So I'm going to have a line from 0 to 2 milliseconds that stops at 0.4. Then I have 40 volts from 2 to 4 milliseconds, but the current is at 0. So when I multiply anything by 0, I get 0. So this line immediately drops down to here. And it's a flat line at the 0 from 2 to 4 milliseconds. Then here I have negative 10 milliamps, and my voltage goes from 40 volts back to 0. So when I have 40 times negative 10, I get negative 400 milliwatts, or negative 0.4 watts. And this is going to end at the 0. So this immediately drops down to negative 0.4. And it ends at the 0. So now I want to find the total energy absorbed by the device from 0 to 8 milliseconds. Well, we know that P is equal to dW dt. So to find the energy, W of t, that would be the integral from 0 to t, P of lambda, d lambda, plus the initial energy, W of 0. We're assuming 0 initial conditions because we were not told anything else. So therefore, we will assume that W of 0 is 0. So since I want to find the integral of this waveform, which is the same as the area under the curve, what I want to do is to find the area under each of these triangles. So for the first triangle, I'm going to have 1/2 times the base, which is 2 milli, times the height, which is 400 milliwatts. For the second triangle, I'm going to have minus 1/2 times the base, which is 4 milli, times the height, which is 400 milliwatts. So the total energy at 8 milliseconds is going to be equal to negative 0.4, and the units for energy are joules. All right, let's look at the final example for today's lecture. In the following circuit, identify which elements are drawn to obey the passive sign convention. B, using the numerical values on the table, identify which elements are absorbing power and which are delivering power. And C, confirm that the law of conservation of energy is satisfied. So first, let's make a column of the elements that obey and the ones that don't obey the passive sign convention. Remember, an element does not obey the passive sign convention if it is not drawn to be a voltage drop. So if we look at this table, the current goes from the negative to the positive for A, so A does not obey the passive sign convention. If we look at B, the current goes from the positive to the negative terminals through B, so B does obey the passive sign convention. For C, the current flows from the negative terminal to the positive terminal, so C does not obey the passive sign convention. For D, the current flows from the negative terminal to the positive terminal, so D also does not obey the passive sign convention. For E, the current does flow from the positive terminal to the negative terminal, so E does obey the passive sign convention. And F, the current flows from the negative to the positive terminal, so F does not obey the passive sign convention. So in order to answer any questions about power, I have to have numbers. So now we have to go to the table. So first, since A does not obey the passive sign convention, the power for A is negative VA times IA, which is negative 8 times negative 4, or positive 32 watts. So that means that B, that element A, absorbs power. For B, element B does obey the passive sign convention, so that's going to be positive VB times IB. So it's going to be positive 15 times 15, which is equal to 225 watts. So we say that element B also absorbs power. Element C does not obey, so that's going to be negative VC times IC. So it's going to be negative times negative 7 times 3.5. So for element C, the power is 24.5 watts. And that one also absorbs. Element D does not obey the passive sign convention, so that's negative VD times ID. So that's negative 10 times 19, which is negative 190 watts. So now we have our first element that actually delivers power, and that's element D. For E, which does obey the passive sign convention, we have positive VE times IE, which equals positive 5 times negative 18.5. So for element E, we have negative 92.5 watts. So that one also delivers power. And finally for F. For F, that does not obey the passive sign convention. So we have negative VF times IF, which is negative 2 times negative 0.5, or positive 1 watt. So element F absorbs power. So far our elements that deliver power are only elements D and E. So for part C, the way that we confirm that this obeys the law of conservation of energy is we see if the sum of power delivered and power absorbed is equal to 0. So there's two ways we can do this. You can sum the power delivered plus the power absorbed and see if it equals 0 watts. Or you can say that the sum of power delivered, the absolute value, must equal to the sum of the power absorbed. So in this case, we're just going to add them all up, and we'll see here that we have 32 plus 225 plus 24.5 minus 190 minus 92.5 plus 1. And when we add all those values up, we see that they equal 0. So this basic circuit element does obey the law of conservation of energy. And this concludes today's lecture on voltage, current, power, and energy.